All right, good day, and thanks for joining me today on physics. And today we'll be looking at electric field intensity. Now, please don't forget to subscribe to this channel and always check your notifications for new videos. So, we'll be looking at electric field intensity today, and the question is, what is electric field? What is electric field? Now, electric field, first of all, electric field is actually the region where electric force is felt or experienced by a charge. So it is a region where a charge experiences a force, experiences an electric force. So that is what we refer to as electric field. Now, basically, when we talk about electric field intensity, we are talking about the extent of the electric field. The extent of the electric field. Now, normally, if we have a test charge, Q naught, let's represent our test charge by Q naught, and we have a point charge, let's call it just Q. Now, this test charge will be, let's assume that our test charge is of a low amount of charge, and this is our point charge. Now, exhibiting what? Electric force. Now, if this test charge is brought within the field, let's assume that this is the field region of this charge. If this charge is brought within the field of this region, it experiences an electric what? Force. It experiences an electric force. So the field intensity at a point is the force that is acting on the test charge. So the field intensity is that force coming from the point charge to the test charge. It is that force acting what? On the test charge. That is what we refer to as the electric field what? Intensity. So we say that electric field intensity is given as the force acting what? On a charge or on a test charge. So it's seen as a ratio, the force to the charge. And the unit of electric field intensity is given as Newton per what? Coulomb. So, so this is what we refer to as electric field intensity. Now, if we remember when we talked about electric field between two charges, we said that the force rather between two charges, the force of either attraction or repulsion between two charges, we said that it is given as 1 divided 4 pi epsilon naught multiply Q1 Q2 over R squared. This is what we gave as the force between two charges. Now, putting this in our equation, we know that the field intensity is given as F divided by Q naught. So we can simply call this Q2 Q naught and call this just Q, since we are making use of our initial example. So when we put this formula for F into this equation, we are having E equals 1 divided 4 pi epsilon naught multiply Q divided by R squared multiply 1 divide Q naught. Because from here, we have that F is multiplying 1 over Q naught. So what we've simply just done is brought out F, multiplying it by 1 divide Q naught. And Q naught goes out. So our electric field intensity can as well be given as 1 divide 4 pi epsilon naught multiply Q over R squared. So this is another formula for calculating what? The electric field what? Intensity. Now, let's look at the lines of force. Let's look at electric lines of force. Now, normally, when we talk about field intensity or the electric field, usually the electric field, let's assume we have a charge, a positive charge. Usually, the electric field is represented by lines of force. It's represented by what we call lines of force. These lines of force actually show the direction of the field. And for instance, if we were to bring a test charge into this field, if we allow the charge to move, the charge will actually move in the direction of the field. If we allow this charge to move, it will move in the what? Direction of the field. So we say that the electric line of force that's what we are looking at. So we say that the electric lines of force is that line that shows the pattern or the lines of or shows the direction of the field when a test charge is placed in an electric field. So if we bring a test charge, for example, let's call this Q naught into here, it will move in this direction. So if for positive charges, the lines of force are moving outward, but for negative charges, the lines of force tend to move inward, tend to move inward. So if we have positive and negative charges, what we'll see as the direction of the field, because what the essence of lines of force is to show us the direction of the field. So what we see as our direction of the field is this. Remember, our positive charge is moving out. So we have a neutral point. We have a neutral point. If we had two charges, two positive charge that will repel each other, this is what we'll have. A neutral point. Now here is called the neutral point, where the electric field is zero at this neutral point. There is no field there because of how these two charges, remember that opposite charges will attract, but like charges will actually repel each other. So here we are having positive and positive, and so the direction of the line of the force indicates that there will be a repelling behavior between these two charges. So if we had, in case, if we had a positive charge and a negative charge, now the lines of force will be this way and showing the direction of the field from the positive region to the negative region. So it's moving from positive to negative. Now, one of the things we must understand when we talk about the electric lines of force is that, one, these lines of force don't intersect each other. There is no way another line would be here. There is no intersection in the lines of force. And normally, it begins from the positive and ends at the negative, or ends at what? Infinity. Then also, we should be aware that the number of lines of force, the number of the lines of the force crossing a surface area is actually equal to the magnitude of the electric field intensity. So if we have En, which is actually the number of the lines of force, the electric field intensity rather, based on the number of the lines of force, because we said that the number of the lines of force is actually equal to the magnitude of the electric field intensity. So we have N, number of lines of force, divided by area. because if we are considering a particular region of space or area, the number of the lines of force there divided by the area gives us the intensity. So now, since n is actually the number of the lines of force, we can also call it the what? Flux, the total electric what? Flux. So we can say total electric flux is equal to n, because we're talking about the flux, we're talking about a number of lines of what? Force. A number of lines of force. So therefore, we can say that the electric field intensity, depending on the number of lines of force, can be given as the total electric flux divided by area. Divided by area. So we've seen another way for calculating what? The electric field intensity. So we are saying electric field intensity is also what? The flux density, or the total flux, electric flux divided by the what? Area covered by the field. So then also we should be aware that the greater the density of flux lines in a region, the larger the what? The magnitude of the electric what? Field. When we talk about magnitude, we are talking about the extent, the strength of that particular field. So if the lines of force here increase in number, for example, it means that the electric field intensity will also increase. So let's see examples of how to solve electric field intensity. Now, suppose we are told to calculate the electric field, calculate the electric field, calculate the electric field at a point 5 cm from a charge of magnitude. The value of the charge is given as 3.2 minus 3.2 times 10 to the power minus 19 coulomb. So if we are told to calculate this, we should remember that 1 divide 4 pi epsilon naught is given as 9 times 10 to the power 9. So we can actually go ahead and calculate what is the electric field at a point 5 cm from a charge having this particular value. So what we simply do is remember that our electric field is given as 1 divide 4 pi epsilon naught multiplied by Q over R squared. So, and we should also bear in mind that our R is given as 5 cm. So we have to change it to meter, which is given as 5 times 10 to the power minus 2 meter. If we convert 5 cm to meter, that's 5 divided 100. So we can go ahead and impute our values into the equation. So when we do that, we're having E equals 9 times 10 raised to the power 9 multiply 3.2 times 10 raised to the power minus 19. Remember, when you are solving, you don't, the negative sign, and this value just indicates that it is what? Negatively charged. That the charge we're talking about is a negatively charged one. So we don't indicate it in our when solving. So we have this 5 times 10 to the power minus 2 to power 2. So when we do this, we're having 9 multiply 3.2 times 10 to the power minus 6. Because this will give us minus 6. So when we multiply this, we say divided by solving this, we're having 25. And when we do this, we have our answer as 1.15 times 10 raised to the power minus 6 Newton per coulomb. Remember that the unit for electric field intensity is what? Newton per coulomb. So this is the electric field intensity from such a charge. All right, let's see another question, another example. Let's see another example. Now, suppose we are given two charges. We call this a positive charge known as Q1 and another positive charge here known as Q2. And a neutral region was located here. So because of both are positively charged, the net effect is what? Repulsion. So the arrows are actually repelling each other. So we have this, and we are given that from here to this point is actually 4 minus x meters, and here is actually x meters. But however, the total meters is actually given as 4 meters. So the question is, what is x? Where is the neutral point between these two charges? If we, in the diagram I gave initially, we noticed that there was a neutral point at the center of two charges. If the two charges are actually equal in magnitude, the neutral point ought to be at the center. But for the neutral point to be somewhere beyond the center indicates that these two charges are not what? Of equal length. And in the question, we're given that Q1 is equal to 14 times 10 raised to the power minus 6, and Q2 was given as 5 times 10 raised to the power minus 6. So these are our values for Q1 and Q2. So the question now is, from what is the distance from the neutral point to Q2? What is the distance from the neutral point to Q1? So what we do now, for the at neutral point, we know that we call this the distance. If we are checking the electric field intensity from Q1 to the neutral point, we label it as E1. And if we are checking the electric field intensity from Q2 to the neutral point, we label it as what? E2. Now, if we at the neutral point, electric field intensity is 0, there is no field there. So basically, what it means is that if we relate this with this, applying it in our equation, we'll discover that E1 will be equals E2. So at the neutral point, the value of E1 is equal to what? E2. At every neutral point, because there is 0 intensity. So we say E1 is equal to what? E2 at neutral point. At neutral point. So if E1 is equal to E2, now remember that our 1 divided 4 pi epsilon naught is also known as K. So we say that KQ1, which is equal to E1 divided by R squared, and E2 is equal to KQ2 divided by R squared. So with this, and if we are saying that E1 is equal to E2, therefore we are saying KQ1 is equal to KQ1 divided R squared is equal to KQ2 divided by R squared. So let's impute our values. Let's impute our values. Now we have K 14 for Q1 times 10 to the power minus 6 divided by the distance of Q1 to the neutral point was given as 4 minus x. So we say all squared is equal to K for Q2 divided by the distance was given as x squared. All right, so our K can go. So we are left with this. Then if we rearrange this, or if we cross multiply, we have 14 times 10 raised to the power minus 6 multiply x squared, which will give us 5 times 10 raised to the power minus 6 multiply 4 minus x squared. So then we can collect like terms, right? We can collect like terms. So we have 14 times 10 raised to the power minus 6 divided by 5 times 10 raised to the power minus 6 gives us is equal to 4 minus x all square divided by x squared. So from here, what we'll have here is roughly, when this goes, we have 14 divided 5, and that gives us 2.8. And if we take out this, we have 4 minus x divided by x, and we can square all together. So taking out the square, we have this. So for us to eliminate this square, it means we take what? The square root of 2.8. So what we have is to take, we are having square root of 2.8 giving us 4 minus x divided x. And here we have 1.67 as the answer to our square root. And we multiply it by x. So it gives us 4 minus x. So what we have is 1.67x. Minus x coming here, we have plus x equals 4. So we have 2.67x because we know that there is a 1 here. So 1.67x plus 1x will give us 2.67x equals 4. So x becomes 4 divided 2.67, and our x is 1.5 meters. So what it means is that from Q1, from Q2 to the point, to the neutral point is actually 1.5 meters. That's our x. Then from Q1 to the neutral point, which is 4 minus x, so that will be 4 minus 1.5. The distance is actually 2.5 meters. So, but if the two charges were of the same magnitude, the neutral point ought to be at the center. All right. So let's look at Gauss law. Gauss law. Now, Gauss law states that the electric flux crossing a closed surface is equal to the ratio of the charge enclosed within the surface. So if we have an enclosed surface, for instance, and with a charge within, the flux or lines of force crossing this charge, crossing this enclosed surface, is actually equal to the ratio of the charge enclosed within to the permittivity of free space, which is epsilon naught. We know epsilon naught to be the permittivity of free space. So if we have a charge enclosed in a surface, and then we have electric lines of force passing, just crossing above the surface, we say that the electric flux, that is the electric flux given as this, is the charge divided by the permittivity of free space. That is the charge within divided by the permittivity of free space. So this is what Gauss's law is stating, that the electric flux as a result of charge enclosed in the surface is given as the charge, the ratio of the charge to the permittivity of what? Free space. Now, if more than one charge is enclosed, then our electric flux becomes the summation of the charge divided by the permittivity of free space. So if we have more than one charge enclosed, let's assume we have this charge, all enclosed. So we sum up all the charges divided by the permittivity of free space to get our what? Electric flux or electric field intensity dependent on the number of electric field lines, because that's our electric flux. Electric flux is like the number of electric field lines over a specified area. So if there is no charge enclosed by the surface, our electric flux becomes, call this electric flux, our electric flux becomes equal to 0 if there is no charge at all enclosed by the surface. Electric charge becomes what? 0. And if we have two charges that are equal in magnitude but opposite, our electric flux is also 0. Now, the total electric flux will be positive if all the charging here is, if the net charge is positive. That is when you've taken the difference and checked all the charges within the surface, enclosed by the surface, and then you, even if you have positive, negative, but the net result after adding is that maybe the positive charges are more than negative charges, the electric flux will eventually be what? Positive. But if the net charge enclosed by the surface is negative, the electric flux will end up being what? Negative. So thank you for joining me today, and please do not forget to subscribe to this channel. Thank See you